What if particles just emerged from energy? What if the structure of reality trembled at the smallest scales? What if reality really isn't smooth at all, but froths and bubbles in a sea of time-chaotic wormholes and intermittent micro-black holes? One man dared to ask such bold questions. Can matter arise without matter, or space become substance? Can energy loop back on itself to create a particle from nothing but a field? Before there was quantum gravity, string theory, multiverses, or holograms, there was a physicist who reached across the fabric of space-time and shaped the questions we still struggle to answer today. John Archibald Wheeler imagined geons, gave black holes and wormholes their names, and gave birth to an idea so unnerving it literally makes you question reality: quantum foam. But perhaps his greatest contribution to physics wasn't theoretical at all. It was human. A mentor to many a great physicist, he helped shape the minds of people like Richard Feynman, who developed the quantum theory of electrodynamics. He also mentored Hugh Everett, who created the many worlds theory of quantum mechanics, and Kip Thorne, together whom which he wrote Gravitation with. He didn't just mold their minds, but rather he introduced the world to many ways of thinking about the cosmos. And perhaps the most profound question that John Wheeler still has us asking is, what if everything came from nothing? A geon is short for gravitational electromagnetic entity. What it is a hypothetical self-contained bundle of gravitational and/or electromagnetic energy that is held together by its own gravitational field. This was Wheeler's attempt at constructing particle-like objects purely from fields and geometry, with no material source. Essentially, a classic field-based object that mimics some features of matter. The core idea is that a geon is a self-gravitating field configuration where there is no point-like particle or external source. The field energy creates space-time curvature, and the resulting curved space-time traps the field inside a localized region. You can think of a geon as a lump of light or a gravitational wave glued together by the gravitational well they themselves create. Some of the mathematical foundations. Of course, we have Einstein's field equations, and you start with the standard Einstein field equations in geometrized units, meaning that we'll let capital G equals C equal 1. And that gives us the Einstein field equations in this form The key constraint for a geon is that the stress-energy tensor must come from the field itself only, not from some external source. Now, for electromagnetic geons, for an EM field given by the tensor F mu nu, the energy momentum tensor is given here by this expression. And so the Einstein-Maxwell coupled system governs the electromagnetic geon. And thus we get the Einstein tensor to look like this, with the following conditions. The field creates curvature, which traps the field, a feedback loop. In his 1955 paper, Wheeler observed that one can consider a metric which on the whole is nearly flat except in two separate regions where a doubly connected region comes into evidence. One of the sketches he provided looked like this, and one can see these doubly connected regions being connected by something that looks like a handle, or otherwise known as a throat. And this model can be used as a basis for building a model of a non-zero classical charge with an everywhere zero charge density. The general divergence-free electromagnetic disturbance holding sway in the space around one of these tunnel mouths will send forth lines of force into the space and appear to have charge. However, an equal number of lines of force must enter into the region of disturbance from the tunnel that it is coming out, and consequently, the other mouth must manifest as an equal and opposite charge. This is what Wheeler meant by charge without charge. So from here, one can go in two different directions. A. We could assume the existence of such structures, such as tunnel configurations, and examine that structure's classical dynamics. Or B. An investigation into the quantum gravitational processes that might give rise to such configurations. Wheeler actually pursued both directions. Now, the classical route led Wheeler, together with his student Charles Misner, to their opus minor, known as classical physics as geometry. Gravitation, electromagnetic, unquantized charge, and mass properties of curved empty space. The quantum route led to the extraordinary tenacious concept of space-time quantum foam. The 1957 paper by Wheeler and Misner was a tour de force wherein the Riemannian geometry of the manifolds of non-trivial topology were investigated with a view of explaining all classical physics. This was a very ambitious project and was one of the very first uses of abstract topology, homology, cohomology, and differential forms in physics. It was the paper that really introduced the concept of a wormhole to the world. Now, Wheeler's aim was to use the source-free Maxwell equations coupled with the Einstein equations with the seasoning of non-trivial topology to build models for classical electrical charges and all other particles and the like entities in classical physics. Classically, it was found that these tunnels would collapse into black holes, and the otherwise interesting topology is hidden behind the event horizon. This is the content of the classical topological censorship theorem, and quantum effects might actually allow us to evade the censorship because time is quite relative at quantum scales. Nevertheless, there are a few qualitative and even quantitative comments that one can make with a certain degree of confidence. Discussing quantum fluctuations in the spacetime metric, Wheeler states the following. The fluctuations in a typical gravitational field potential is delta G approximately equal to the square root of h bar G over c cubed, all divided by L. So the length L plays a major role in the metric fluctuations. So the fluctuations will be inappreciable in comparison to typical average values of the metric G approximately equal to 1, so long as the distances L under consideration are substantial in comparison with the Planck length. Now, in later publications, the gravitational field fluctuations are concluded to have qualitatively new consequences at distances of the order h bar G over c cubed to the 1/2 power, or 1.6 times 10 to the negative 33 centimeters. So, what is the origin of such claims? Well, they are based on the fact that we believe we understand the quantization of linearized or weak field Einstein gravity. Rephrasing the classical linearized gauge-fixed Einstein equations as follows. These equations can be derived from an action principle given here. Now, this classical linearized gauge-fixed action can also be extracted directly from the Einstein-Hilbert action by expanding out the Ricci scalar to second order in h mu nu. And proceeding in that manner is more fundamental, but also somewhat more tedious than our present discussion. Now, since the linearized action is quadratic in h-bar, quantization can immediately be carried out by making an analogy to the free scalar field. The stress energy tensor is, for the time being, considered to be a fixed classical external field. The situation is in complete analogy with the quantization of the electromagnetic field in the presence of a fixed classical current. One is immediately led to consider the two-point correlation functions such as the following here: the trace-trace, the tensor-trace, and the tensor-tensor correlation functions in quantum field theory. When the externally imposed stress energy is 0, the first of these two-point functions is the trace-trace correlator is immediately calculable in terms of the scalar field two-point function. Expectation value here is dependent on the Planck length, the square of the Planck length. Thus, at a distance scale L, the quantum fluctuations in h are of the order the square root of the expectation values here, where that constant can be negligibly ignored. And when we get to the tensor trace correlator, which is somewhat more complicated, one can use the symmetries of the background Minkowski space to deduce that this correlator must be of the form given here. And here z is defined as the difference between x and y. So by translational invariance, the correlator can depend only on this difference z, and the coefficients a and b are dimensionless constants. Now, the expression embraces, given here with the constants a and b incorporated, is the most general dimensionless tensor that can be constructed solely out of the flat Minkowski metric and the relative separation z, which also has the correct symmetry properties. And finally, the tensor-tensor correlator is considerably more complicated. The Minkowski metric is our background metric, and it has symmetries which allow us to deduce that the correlator must be of the form here. Again, z being equal to x minus y, the difference, the relative difference. So qualitatively, that is, ignoring the messy tensorial structure, the weak field metric perturbations can be estimated as approximately delta h mu nu at the length L, approximately given here, and expressed in terms of the metric tensor components themselves. It is often convenient to leave out the factor of the square root of 8 over pi and just give the metric fluctuations to be relatively of the order the Planck length divided by L. So let's go over what you do to calculate the metric fluctuations. Investigating how the space-time geometry deviates from the background metric is the goal in calculating metric fluctuations. 1. You assume a known background metric, and here we can assume the Minkowski metric, or one can assume the Schwarzschild metric. Then one defines the fluctuation of that metric, where we have a small perturbation h mu nu in the metric, giving us qualitatively and quantitatively the metric fluctuations. Then what you do is you expand the Einstein-Hilbert action, which is given here, r being the Ricci scalar, and expanding to second order in our little metric measuring the fluctuations, which gives the quadratic action for the fluctuations. And this step is central for studying things like graviton dynamics and linearized general relativity, or loop corrections to the effective action, also with gauge fixing. The third step is then to take the linearized field equations and By varying the expanded action with respect to h mu nu, you obtain the linearized Einstein equations. So here we see that the variation in the vacuum where the stress energy tensor is equal to 0, this yields wave equations for the perturbations. And that is, in flat spacetime, the weak field limit, the linearized equations will reduce to this in harmonic gauge. And h over bar, given by this expression, where just h is the scalar value of that metric fluctuation. Then we quantize the metric fluctuations. That is, apply the quantum field theory on the curved spacetime. You treat the metric fluctuation h mu nu as a quantum field, decompose it into modes, that is, plane waves with spherical harmonics, and then you apply the canonical or path integral quantization process. Then you start to use that to compute correlation functions, such as this on the vacuum energy state, and in quantum field theory, it's called calculating the two-point correlator functions for the graviton field, otherwise sometimes called the graviton propagators. So that kind of summarizes the details. Well, of course, then once you have all this, you can compute the fluctuation observables. That is, depending on the context. In cosmology, one can compute something called the power spectra of the fluctuations from inflation. And in semi-classical gravity, you can evaluate the expectation value of the stress energy tensor and feed it back into the Einstein equations to study the back reaction on spacetime. Wheeler was very fond about learning the back reaction of certain processes. A scalar-induced fluctuation refers to a disturbance in the spacetime metric or energy distribution caused by fluctuations in a scalar field. A scalar field phi has some sort of quantum or classical fluctuations, delta phi, which then these fluctuations source the Einstein field equations and induce the corresponding fluctuations in the metric g mu nu. The result is a scalar-induced fluctuations of the spacetime geometry.
Radiation, a pencil of radiation, carries energy with it, and energy has mass, and therefore a pencil of radiation must exert some attraction on things beside it. What about getting a pencil of radiation curved into a circle so the light goes round and round? Then the attraction it exerts is concentrated as if at the center. So what is it that bends this circle, this pencil of radiation into the circle? It's the gravitational attraction of the pencil of radiation itself. That was the idea of the Geon. Actually, if you think of different possibilities for the size of that Geon, bigger or smaller, you find that if it's very big, the energy is low. To push the radiation together requires energy. And you climb a hill like the hill of a volcano until you've come to a maximum energy. And then if the pencil radiation becomes any smaller in size, the energy starts to go down and the thing collapses. So a Geon is really an unstable entity. It either blows up into a cloud of radiation traveling away in all directions, or it collapses into a totally collapsed object, something that we today would call a black hole.
At distances below the Planck length, quantum fluctuations are large, so large that linearized theories will break down. The quantum physics is full of non-linearity, non-linear Einstein gravity. Quantum effects make classical gravity break down once your distance scales below the Planck length. And a few more words about the quantization of linearized gravity are in order. It is possible to put the linearized action into a form more suitable for discussing the quantum field theory by inducing the variable f mu nu, which is a multiple of h mu nu, and we can express it here and then calculate the action. And in the absence of matter, the model reduces to the quantum field theory of a free massless tensor field, a free massless spin-2 field, i.e., a graviton. In the presence of matter, the remaining pieces of the linearized action describe a quite ordinary, non-renormalizable quantum field theory. The theory is known to be non-renormalizable because of the appearance of the dimensional coupling constant, kappa. And here you see its value is 16 pi h bar raised to the 1/2 power over the Planck mass times c, the speed of light. On the atomic scale, the metric appears flat, as does the ocean to an aviator far above. The closer the approach, the greater the degree of irregularity becomes apparent. Finally, at distances of the order of Planck length, fluctuations in the typical metric component g mu nu become of the same order as the metric themselves.
Nobody who deals with radiation or molecules can be unaware that in a molecule, say the hydrogen molecule with 2 hydrogen atoms, even at the absolute zero of temperature, those 2 hydrogen atoms are not sitting quietly at a fixed separation from each other. They're wiggle-waggling the so-called zero-point energy, a minimum irreducible energy that can't be got rid of. And that same feature of minimum irreducible activity obtains for the electromagnetic field through space and the gravitational field. It's wiggle-waggling all the time. What we think of as smooth, simple space is really a wiggly business. I don't know any better image for it than the look of the ocean as one comes down from a plane high above the ocean. It seems to be a perfectly smooth surface. You come down closer, you see the waves, and as you get still closer, you see the waves breaking, and you see foam. And I think it must be the same in the geometry of space. If for all our everyday experience, the geometry of space is smooth and flat, but as we examine it more closely, it must show oscillations. And still more closely, it must show foam, a foam-like structure. And that means that down at the very smallest distances, this idea of before and after really lose their meaning. At very small distances means what? Well, it's so interesting that Max Planck, the great German physicist who had done so much to understand radiation and set us on the track to the quantum, Max Planck had, in the study of radiation, recognized a new constant of nature. And that constant, combined with the known constants of nature, the speed of light and the constant of gravitation, define a certain standard of length, a certain standard of time, a certain standard of mass. Planck's notation is not quite in tune with today's, but if you tune it into accord with today's notation, you find yourself led to a length and a mass and a time, which I called the Planck length, the Planck mass, and the Planck time. And it's at that enormously small scale, fantastically small scale, that space has this, must have this foam-like character. Will we see any evidence of that in time to come? We surely will, but I'm not bright enough to see just where the first key test will show up.
Once the metric fluctuations become nonlinear and strongly interacting, the analogy with the surface of the ocean suggests that the metric fluctuations might break in a manner analogous to the breaking of ocean waves encountering the shore. This might be expected to endow space-time with a foam-like structure. Space-time resonates between one foam-like structure to the next. Space-time foam, or quantum foam, means that space-time topology might be constantly fluctuating. Two quick and dirty arguments. Consider a quantum particle that is confined to a region of spatial extent L. Then the Heisenberg uncertainty principle will give us that delta P times delta L is approximately in the order of h bar. On the other hand, special relativistic effects might imply that the change in energy, delta E, is approximately of the order given here, which is approximately c times delta P. The Newtonian gravitational potential phi near the edge of the confinement region is then of the order g total mass over L, which approximates, through simplification, c squared times the Planck length over L squared. So then one has that the metric fluctuation is of the order LP over L squared. The extra factor here is not surprising. On the other hand, we previously got an estimate of LP over L, and now we have LP over L squared. The distance that we are working in one case, we are looking at correlations in quantum fluctuations, while in the other we are looking at the gravitational effects of confining a physical particle to a small region of space. It's a dynamic versus static configuration difference. Now, the difference can be seen as the difference between virtual gravitons versus real physical particles. Either style of argument implies that the change in the metric is approximately 1 at the Planck scale. And a second quick and dirty argument is given by saying that to any particle-like object of mass m, it is possible to assign 2 fundamental length scales, the Schwarzschild radius and the Compton wavelength. The Schwarzschild radius given here and the Compton wavelength being given here. For all elementary particles whose physics is dominated by quantum processes, the Compton wavelength dominates. However, for systems whose physics is dominated by the classical gravity, then the Schwarzschild radius is what dominates. And for systems for which the Schwarzschild radius is approximately the Compton wavelength, implying that the mass is approximately the Planck mass, it seems that they are in the quantum transition zone, the region between quantum and classical regimes. Quantum fluctuations of the gravitational field are expected to be important and non-trivial once your scale is below the Planck length, or your energy is larger than the Planck mass. Topological considerations. One has to consider changing topologies in the realm of quantum foam. A critical aspect of the space-time foam picture has been glossed over, meaning that geometry and topology are different animals. The question of what happens when quantum fluctuations become too large is a reasonable question. While there is no reasonable disagreement that the geometry of space-time undergoes quantum fluctuations, there hasn't been any agreement on whether or not the topology of space-time also undergoes quantum fluctuations. Or does it? Does the topology of space-time fluctuate? What does it mean for the topology of space-time to fluctuate? Wheeler argued forcefully in favor of topological change below the Planck length. And for those of you who are not sure what I mean by topological change, I mean that you allow for holes in space-time. A sphere can become a donut. Wheeler asserts that the values of the metric fluctuations comparable to unity and larger indicate changes in the geometry so drastic that the word curved space-time is hardly adequate. In other words, the fluctuations are so violent, one would have a hard way of classifying that as curved. If we argue from the Feynman functional integral formalism, Wheeler then states, because it is the essence of quantum mechanics that all field histories contribute to the probability amplitude, the sum, not only may they contain doubly and multiply connected metrics, but it must do so. General relativity, quantized, leaves no escape from topological complexity. There are some words of caution we must take here. In a fixed space-time, does topology of space change as a function of time? Do different space-time topologies interfere quantum mechanically? Now that second one is pretty deep. But topology change is a very fundamental question to the existence of wormholes. If one views the Lorentzian metric as paramount, then the very existence of the metric imposes topological restrictions on the spacetime itself. In a causally well-behaved classical spacetime, the topology of space does not undergo change as a function of time. However, in a causally ill-behaved classical spacetime, the topology of space, well, it may be subject to change. Classically, spacetime is modeled by a single Lorentzian manifold. This manifold, whatever it is, if fixed, and spacetime and its topologies cannot be said to change in any meaningful way, then that leaves the quantum realm for us to work with. Working within a single Lorentzian manifold, if one has some natural definition of time, one can cause the time function to slice up spacetime into a set of hypersurfaces which might be thought of as quote-unquote space. One might ask if these three-dimensional slices of spacetime change as a function of time. And such an attempt does raise the question what class of time functions would be acceptable. Does the topology of space change in any intrinsic way? At the smallest scales of reality, spacetime is anything but smooth. It churns, twists, and fluctuates in a sea of uncertainty, a quantum foam, where the fabric of the universe bubbles with possibility. And within those fleeting microscopic throats of curvature, a tantalizing idea persists, that wormholes, bridges between distant regions of spacetime, might be born not in science fiction, but in the quantum tremors of the real world. Could these ephemeral tunnels be stabilized, expanded, or engineered? For now, the answer remains hidden in the froth of the Planck scale, where gravity and quantum mechanics dance in paradox. But if we dare to listen closely, the foam might be whispering the future of interstellar travel, and maybe, just maybe, a path through the void itself.